So shall we start the speakers? So Erica, would you introduce the speakers? Thank you.
Yes, please. Sure. So the first speaker is Jia Deng, who is an associate professor of computer science at Princeton and directs the Princeton Vision and Learning Lab and works on computer vision and machine learning.
Thank you, Erica. Should I get started? Can people hear me?
Yes.
Yeah, loud and clear.
Okay. Okay, so let me go ahead and share my screen. So is this working now? Can people see my screen?
Yes.
Okay. Cool. So let me get started. Today I'll talk about foundation models for material synthesis. I mean, this is a very big title, but you know, the talk actually just will cover a little bit of what we want to do and what our technical foundations. So this is a project that's in collaboration with Professor Julie at MIT. Just a little bit more about the PIs. So myself, I'm in computer science from Princeton, and Professor Julie is Professor of Material Science and Engineering at MIT. And so here's what we are hoping to do. This is sort of the ultimate goal, that is to be able to do automated material synthesis. So we call this system AutoMS, and we hope that it will accelerate material science research. And when we have this overall diagram about what we're hoping to achieve, we're sort of a goal that's a smaller scale, which is that we're hoping that we could take synthesis recipes described in text and be able to predict what kind of material structures we're going to get from the recipe. Particularly, the material structures are described in terms of images and attributes and statistics from those images of the material structure. And if we're able to make accurate predictions, then in turn, given a desired structure, say some kind of attributes or statistics in terms of images, we can also solve the reverse problem, that is to propose synthesis recipes that can give you that structure. And so the prediction and proposal part are we hope that can be done by foundation models and can be automated and to help material science research. And obviously, we want this to be validated and integrated with the real world lab. So the predictions would be compared with real world outcomes, and also the proposing recipe would be carried out physically in actual material science lab. So that's the sort of just a very high level overview of our goals. And so we have sort of been working on this just for a few months. So unfortunately today I actually don't have any research results I can show in public. So instead, I'm going to just tell you a bit about sort of our technical foundations. So the prior work that we have done and we're going to build upon for this project and for these goals. So there are two parts I'm going to talk about. The first part is on the Princeton side, and this is about the use of symbolic knowledge in neural networks. Specifically, we have something called the optimization-inspired architectures, which involve a combination of deep learning and optimization approaches, and it involves special differentiable optimization layers that are embedded in recurrent neural networks, and I will go into some detail about this, and then I'll talk about the MIT side, which includes integration of foundation models into the material science workflow, specifically automated robotic workflow and a co-pilot Professor Lee's lab has built for real world, to help real world experimental scientists. Okay, so let me start with the use of symbolic knowledge in your networks. Here I'm going to sort of deviate a little bit from material science, just talk about a very different problem. However, the general principles, I believe, will work very well in the material science domain. I've worked a lot on computer vision, in particular 3D vision. So here this is one example of 3D vision. So the problem itself is formulated as taking an input of a video and output a 3D map and camera trajectory. So here's example input video, just a monocular RGB camera. And you'd like to basically reconstruct the 3D structure of the scene and also figure out the trajectory of the camera. So this is a fairly standard problem in 3D vision and robotics. Now, how would you solve this problem? Classically, we typically use an optimization-based approach. This is based on sort of symbolic knowledge we have about multi-view geometry. In particular, if something in 3D is moving and it will be projected into a 2D image through your camera, and because your camera is also moving, so this will result in 2D motion, also called optical flow. And because we understand the physics and geometry pretty well, especially in terms of image formation, and so the 2D motion that you observe would be a known analytical function of 3D points and your camera motion. So in other words, we could write an equation that says the observed 2D motion is a function of the 3D structure and the 3D motion. So this effectively gives us a constraint that we can use to solve the problem. So the details of the equation are not the point here, are not important for the purpose of this talk. The important point is that there is an equation that we can write down, and this is the symbolic form. So you can do sorts of good things like deriving the derivatives, and you can formulate an optimization problem which says, okay, if I want a solution, let's say I want the 3D points and 3D motion, my solution has to satisfy these constraints, and I can formulate an optimization problem, right? That's here the step 2, which is that if somehow I could know the 2D flow, which I can maybe estimate to by comparing pixels across frames, and then once I know the 2D motion, and I can solve a optimization problem that says, okay, the 3D structure that I seek has to satisfy this equation, and in particular, I can say the left side of the equation has to be as close as possible to the right side, and then this gives me a optimization problem, minimizing the difference between the left side and right side. I can solve it with some standard optimization algorithm. However, one problem with this approach is that often this constraint alone does not constrain the solution space enough. So you could have false solutions that you don't actually want. So in fact, you need to sort of further regularize this optimization objective. However, it's not usually clear how to formulate the regularization. So generally, you would sort of handwrite some heuristics, but it's kind of hard for heuristics to cover all the corner cases. So and people sort of have tried a different approach, which is just purely based on deep learning. So you basically have a lot of training data, input out the examples, and then you just apply a standard architecture that maps the input to the output. This will work to some extent. However, they are not nearly as good as the classical optimization-based approaches. So here's just some benchmark results that show you that the classical optimization-based approach actually works a lot better. It's a lot more reliable than these vanilla deep learning-based approaches. So here we tried to combine the best of both worlds by using both neural networks and the optimization-based approaches. So as a result, we had a system that was state-of-the-art and achieved very large improvements over all the prior systems. So here, we'll just give you a general idea how this works. There are two key components. One is recurrent updates, and another is differentiable optimization layers. So here's the overall architecture. So basically, it's still neural network based at the out sort of the sort of the main thing. It's still a neural network. However, it's a recurrent network. You can think of the recurrent network as acting as an optimizer that does iterative refinement of a solution. Basically, it takes the initial solution and perform iterative updates, and each update is a recurrent network. And it's kind of similar to gradient descent, although there is no explicit optimization objective written here. So the network basically learns to do optimization. And then inside this recurrent update, there is a special layer that's basically a differentiable optimization layer. So it solves an optimization problem to enforce certain constraints between the variables. And then this layer itself is made fully differentiable. And so you can do backpropagation on it. And so in this case, there's a DBA layer. I'm not going to the details, but what it does is try to sort of enforce the no geometric constraints. And then also there are still a traditional neural network. In this case, it's convolutional GRU inside this update operator. So this recurrent network actually sort of gives outputs to the optimization layer, effectively specifying the parameters of the optimization layer. So you can think of the role of the network, the recurrent network here, as sort of two folds. One is to try to directly predict certain variables that are not covered by the optimization, or supply additional constraints. And that's the first aspect. The second part of its job is to kind of guide the optimization. So you actually also predict, let's say, the trust region size. If we solve if inside the optimization layer, we do, let's say, Gaussian-Newton iterations. So inside this optimization layer, we'll basically be solving a optimization objective, and in this case, a nonlinear least squares, which we linearize as we use with Gaussian-Newton steps, and then because we have linearized it, we can have a differentiable closed form solution. Okay, and this layer is made fully differentiable. So that's the basic idea. So this is relevant to material science and other scientific domains because we do have a lot of symbolic knowledge, right? We have these invariances and sort of equations that are in compact symbolic form that we can make use of for many different tasks. And okay, so now moving on to the second part of our technical foundations. So that's on the MIT side, which has done a lot of work on integrating foundation models into the material science workflow in the real world material science lab. So I'm not an expert on material science. So here I'm just gonna play some very cool videos that Professor Lee's lab has made to demonstrate the work. So here's the first one. So let's demonstrate the robotic system that's automated. So basically, in the lab, they have these sort of uh, so every step of the workflow uh, is automated. However, you still need a sort of a brain to decide what to do, right? So actually, they have also done some very cool things in that aspect, integrating with foundation models. So here's a system called Crest that they have developed. Okay, I won't play the entire video because this might be too long. And there's another so here's another part of the system, which is that they could actually use this copilot uh, for image analysis in material science. Okay, I won't play the entire video. So basically, the Professor Lee's group has a YouTube page with lots of very cool videos, and I encourage you to check them out. And that's all of my talk. And thank you. And if there's time, I'm happy to answer some questions.
Great. Thanks, Jaya. This was great. Actually, I was not familiar. I know Julie quite well, so you learn about what your friends are doing, at these kinds of meetings. I'm wondering how you're imagining integrating sort of this symbolic knowledge in material synthesis, because I mean the problem space that you sort of describe with SLAM and stuff, right, is sort of continuous dynamics, and synthesis has sort of many sort of discrete elements. So I was just curious how you're thinking about encoding that knowledge in there.
So I think that's a good question. So I think the general principle is not actually restricted to continuous domains. If we have discrete quantities, we can still come up with ways to handle them. Obviously, the optimization would be harder, but I think that there's already like relevant work on how that can be integrated with neural network. For example, I think that there are things like SAS solvers that are integrated with neural networks. So I think technically that's possible. So I think that itself poses very interesting technical questions that we would like to explore as well.
Just another kind of follow-up question on the droid SLAM model. So you mentioned that it can like enforce constraints that are from like kind of the known physics. I think it's the big F in your equation. Are those constraints being forced in kind of like as a hard constraint, or is it more of a soft constraint? And are you able to get like good numerical accuracy on that, or like how does that trade-off work? Because I think there's a paper from our group a couple of years ago from Varun doing, where he was basically looking at the difference between enforcing it was curl in fluid flows using soft constraints versus hard constraints, and basically what that I think soft ended up not quite conserving energy totally.
Right. So this can be either hard or soft. That can be a design decision, because if you want to make soft, so basically, so the layer solves the optimization problem. The optimization problem has some parameters you still have to specify, or in other words, has some like input, right? So like the coefficients of there's parameters in your objective that need to be given externally, and those can actually be given by the neural network itself, can be predicted, or can be hand coded. So in fact, can also actually be learned. So in fact, in our framework, you can have training data, and then the the network can actually learn how to specify the optimization problem. Maybe it will find that it helps to make the optimization constraints hard or soften it. This can actually be a data-driven thing.
Great. So Jia, if you have time, there is if you click the Q&A bar, there is a question. If you can just answer it live, you can type it when you have time. I think, yeah, with that, we can move on to the next speaker. But thank you very much for a very interesting talk.